Good morning. Okay. So good morning. My name is Patrick Tardivel. I work in the Institute of Maths in Wrocław, and I'm going to give a talk on screening rules for LASSO. I would like to say that I'm really happy to participate for this grand premiere of one-word seminar in statistical learning. And so in this talk, I'm going to introduce some screening rules. Screening rules for LASSO appeared in the literature 5 or 10 years ago. And I'm mainly going to introduce some well-known screening rules, like strong rules, safe rule, dual projection polytope rules. And now I'm going to be a bit more precise on the notion of screening rules. So, in the first expression, this one, it's actually a penalized least square optimization problem. So in this problem, X is an enthalpy matrix, frequently called in statistics design matrix. Y is a vector in Rn, frequently called response. And this optimization problem is in this optimization problem, we minimize with respect to B, the residual sum of squares, this part, plus the penalty term. So the penalty term is a norm. And in the particular case in which the norm is the L1 norm scaled by the tuning parameter, we obtain the LASSO optimization problem. So two things I want to stress. The first one, for this talk, actually, I do not assume that minimizer is unique. It's not relevant to assume actually that minimizer of LASSO or more generally minimizer of penalized least square optimization problem is unique. So that's why I have this notation, and potentially this expression can be a set and not just a single vector. And the second thing also, I'm going to mainly focus on LASSO. And so mainly I'm going to be interested by this optimization problem, but some properties I'm going to give actually are also available, are also true for the penalized least square optimization problem. And in particular, these properties are also true for slope optimization problem. Now, to be a bit more precise on the notion of screening rule, okay. If I know that one component of LASSO is equal to 0, the component I of LASSO is equal to 0, then actually I can recover the LASSO minimizer by solving this last optimization problem. In this last optimization problem, the component I of B is equal to 0. Thus, it is an optimization problem on a p-1 variable. We say also that in this case, we discard the column I of the matrix X. And of course, when we are able to discard a lot of columns of the matrix X, this optimization problem takes less time to solve than the usual LASSO problem. So there is, for computational time, it's relevant to be able to discard some column of the design matrix X. Now I'm going to give characterization of minimizer of penalized least square optimization problem and thus of LASSO also optimization problem. So to give this characterization, first I need to introduce briefly the dual norm. So given a norm, the dual norm, it's a norm with a star, computed at X, is actually the largest scalar product between U and X, when the norm of U is smaller than 1. And with the dual norm, I have a characterization of a minimizer of penalized least square optimization problem. So at beta is a minimizer of a penalized least square optimization problem if and only if these two expressions hold simultaneously. Okay. Now, in the particular case of LASSO, the dual norm is actually the the supremum norm, and that's why actually I obtain this expression for LASSO, because the dual norm of the L1 norm is the supremum norm. And actually this expression is an equivalent way of this scalar product is equal to the L1 norm. Based on the characterization for LASSO minimizer, I obtain two relevant properties. The first one is the LASSO minimizer is equal to 0 if and only if the supremum norm of x prime y is smaller than the tuning parameter lambda. The second actually relevant property is this one. When this inequality occurs, then the component j of the LASSO is equal to 0. And now I'm going to introduce strong rules. And before to introduce strong rules, I'm just going to give an illustration of LASSO solution path. On this picture on the left, so on the x-axis represents the tuning parameter of LASSO, y-axis represents LASSO estimates, and we have 4 curves. So it means that for this particular very simple example, LASSO estimator are just 4 components. So you may notice, for example, that for the LASSO solution path, each curve is piecewise linear. You may notice also, and on the right, so it's another illustration. Actually, on the right, I illustrate this kind of curves. Yeah, this kind of curve, this one. Okay. And actually, so you may notice for these curves are piecewise linear. You may notice also that, okay, these 4 curves lie into an angular area. So the above is the line y equal lambda, and below is the line y equal minus lambda. And you may notice that when the curve is not on the boundary of this angular area, it means that the component of the LASSO is equal to 0. So equivalently, when the curve is not on the boundary on this angular area, it means that this expression, so line expression, is in absolute value smaller than lambda, strictly smaller than lambda. The strong rule is actually an heuristic rule, so it's based on the empirical fact that, or empirical observation, I should say, that most of the time, this function, this one, is one Lipschitz. So very, very frequently, for a lot of design matrix, this function is one Lipschitz. So you may notice that actually this function is piecewise linear. So it's differentiable for almost every lambda. And one Lipschitz just means that when the derivative exists, the derivative is in absolute value smaller than 1. And if we assume that actually it's not always true, we can find actually counterexample in which this function is not piecewise linear. But if we assume that, we can derive really simple rule, which is a strong rule. I'm going to illustrate a bit more now. Okay. So here I assume that this function, this one, are one Lipschitz for every j, and under this condition, when this expression, when this inequality occurs, then the component. Yeah. Okay. When the component j of the LASSO is equal to 0. Okay. So here, for example, in these figures, so when lambda is equal to the supremum norm of x prime y, okay, then the lasso estimator, this one is equal to 0. Okay, and thus this function is equal to x prime y. So at lambda equals this value, when lambda equals this value, this one, this function is equal to this expression, but without absolute value. Okay? I did a mistake with absolute value here. And now, if in addition I assume that this function are one Lipschitz, for sure, the curve of this function is going to be lies into this rectangular area, this area. Okay? Because it's lying the, okay. And you may notice that when lambda is actually in the right segment here, then for sure this curve does not lie on the boundary of the angular region. Or say differently, in absolute value, this expression is smaller than lambda. And thus the component j of the lasso is equal to 0. And actually, when I say that lambda in this red area, equivalently, I can say that this inequality occurs. But strong rules, there is also. Strong rules are also applied sequentially for a sequence of tuning parameters. So you have a decreasing sequence of tuning parameter, and given the lasso minimizer, assume that we compute the lasso minimizer at the tuning parameter lambda k. When this inequality occurs, then we deduce that the component j of the lasso is equal to 0. Okay. So this rule, strong rule, works under this assumption that this function are one Lipschitz. So the derivative is an absolute value, I mean smaller than 1, for example. Okay, it's not always true. I can actually hear some people, but okay. And okay, so it's not always true that this function are one Lipschitz, so that's why actually strong rule is much more an heuristic rule, which works well, but it's not a foolproof screening rule. And now I'm going to introduce actually screening rules which are foolproof and which work in any case, whatever the design, whatever the tuning parameter, always work. And first I'm going to give actually a result which is a Keystone result for screening, foolproof screening rules. So I'm going to introduce this proposition. This proposition actually generalized to penalize least square optimization problem, a well-known fact for LASSO. So in this proposition, point 1 claims that the minimizer of penalized least square optimization problem is the null vector if and only if the dual norm between of x prime y is smaller than 1. And for LASSO, it's actually, we obtain the supremum norm of x prime y is smaller than the tuning parameter, lambda. And point 2 claims that actually this vector, HU, is actually the projection of y onto this convex set. I did an illustration of this projection So here the convex set is actually an ellipse, but generally speaking, this convex set is actually a polytope. For example, when it's the one for LASSO, this the dual norm is a supremum norm, and thus this convex set is a polytope. But just to give a sketch of the proof, which is really, really simple. So it actually, we want to check that HU is a projection of Y onto this convex set. And to do that, we just need to check that the scalar product between these two vectors is non-positive. And when we compute the scalar product between two vectors, when U is an element of this convex set, actually lie in the convex set, we obtain this expression quite easily. And now when you obtain this expression, in the first expression A, it's easy to see that the scalar product between two vectors is always smaller than the norm of the first vector times the dual norm of the second. And here actually, the dual norm of x prime u is smaller than 1 by assumption. In addition, according to the characterization of minimizer of penalized least square optimization problem, this scalar product is equal to the norm of beta. So that's why actually at the end we obtain that this scalar product is negative, is non-positive, and thus HU is actually the projection of Y onto this convex set. Now, if I focus more on LASSO, with this result, in particular for LASSO, we obtain exactly this result, which was actually introduced a long time ago by few years ago by Ryan Tipshiani and co-authors. So the LASSO residual, which is this vector is actually the projection of Y onto this convex closed set called LASSO null polytope. And now, this proposition, this one, is really useful to establish that this inequality. And as soon as we have this inequality, it means that the component J of the LASSO is equal to 0. Why it's useful? Mainly because we know that this vector, this one, lie actually in the LASSO null polytope. And thus we just need to find an upper bound of the scalar product between the column J of X and this vector, which lie into the LASSO null polytope. So now I'm going to give some foolproof screening rules. The first one is actually a safe screening rule. So for safe screening rule, when this inequality occurs, then for sure the column J of the LASSO is equal to 0. And you may notice actually in this inequality that when lambda on the right side, when lambda is the supremum norm of x prime y, and I evaluated for this lambda, I just obtain x prime y, the supremum norm of x prime y. So of course, when lambda is larger than this expression, this inequality occurs, and thus this safe rule confirms also the basic fact, the well-known fact that when lambda is larger than this expression, the LASSO minimizer is equal to 0. I'm going to illustrate this safe rule in the particular case in which column of X are normalized. So L2 norm of column of each column is equal to 0, is equal to 1. So here on the y-axis, we have the tuning parameter lambda. And the red curve is the curve of this function, the one which appears actually in the safe rule. And you may notice that when lambda lies into the red segments, this function, this expression is larger than the supremum norm of is larger than the scalar product between the column j of x and y in absolute value. And thus, when lambda is lie into this red segment, according to the safe rule, the component j of the lasso is equal to 0. We can say we know also that under this assumption, when columns are normalized, when columns are normalized, we know that actually when the safe rule discard one column of x, then the strong rule also discard this same column, the same column. And thus it means that the safe rule is more stringent than the strong rule. And now I'm going to introduce another screening rule, which is actually the dual projection polytope rule. Okay. So, according to this screening rule, when this inequality occurs, then the component j of the lasso is equal to 0. Again, you may notice that in the right side, when lambda is equal to the supremum norm of x prime y, this expression is thus equal to also the supremum norm of x prime y. And thus, when lambda is larger than this expression, this rule obviously occurs. And thus also this screening rule confirms the well-known fact that when lambda is larger than the supremum norm of x prime y, lasso minimizer is equal to 0. Again, I'm going to illustrate this result in the particular case in which column of x are equal, for the L2 norm are equal to 1. Okay. So again, it's similar. Here we have on the x-axis is the tuning parameter lambda. On the y-axis, the blue curve is the curve of this function associated to the dual projection polytope rule. And you may notice that when lambda is in the blue segment, actually, this function is larger than the scalar product between the column j of x and y in absolute value. So when lambda lie into this blue segment, then for sure the component j of the lasso is equal to 0. We also know that under this assumption, the dual projection polytope rules. Under this assumption, I want to say when the safe will discard one column of x, then the dual projection polytope rule also discard the same column. Thus, the safe rule is also more stringent in this case than the dual projection polytope rule. So it's the last slide of my talk. So thank you for listening.